Hi guys, in last lesson you were introduced to indicial equations, which are equations where the unknown, the variable, is in the power. So this is supposed to support last lesson's content. We'll have a look at indicial equations through a whole series of examples. But before we do that, let's have a quick look at what it means to be an indicial equation. Over here we have a to the power of x equals a to the power of y. So when we have this situation, we should be able to conclude that x is equal to y. Okay, so indicial equations work on this basis. Now notice that we have a very specific set of circumstances. We have a base raised to a power equal to a base raised to a power, and it's the same base. And it's only then can we conclude that the powers must be equal. And that's just a matter of common sense, I think. Now, if we change that at all in any way, shape, or form, then it doesn't follow through. So, for example, if I had 2 times a to the power of x equals a to the power of y, then we cannot conclude that x is equal to y because they're different. Or if it was a to the power of x equals b to the power of y, then we cannot conclude that x equals y or anything else. We just can't do it. Even if we have a times a to the power of x equals a to the power of y, then we can't conclude that x equals y, although in this instance there is something we can do to make it work. So the name of the game with indicial equations, always, is to change the equation if you can, so that we have a base to a power equaling the same base to a power, so that then we can set the powers equal to each other like so. And so the following examples will take you through that process. So let's have a look at example 1 on slide 3. We have 2 to the power of 3x equals 2 to the power of 9. We have a base of 2 here and a base of 2 here and nothing else around. And so we can conclude, and we do it by writing the therefore symbol. I'll use black so it's the same color. So we can say, therefore, 3x is equal to 9, like so. So we're just equating the powers. And now we solve the equation just like we normally would do. I'll spell it out so that we're all good with it. We're going to divide this side by 3 and divide this side by 3. That gives me x all by itself, and 9 divided by 3 is 3. And so we conclude that when x is equal to 3, 2 to the power of 3x is equal to 2 to the power of 9. Okay, let's have a look at example 2. Now this is not in the right format. We've got bases of 2 here, but this is 2 to the power of 3x times 2 equaling 2 to the power of 10. So it's not in that format of a to the power of x equals a to the power of y. It's not that simple. But we can simplify it until it is. So if you want to, pause for a moment and see if you can figure out how you would go about changing this equation, particularly the left-hand side, so it's in the right format, and then I'll continue. Okay, you've either had a chance to have a look at it or not by pausing. So this is what we do. We simply, now I'll do this bit in my head, I wouldn't actually write this down, but just to spell it out for you. 2 is just 2 to the power of 1. So I'm just going to literally write the 1 in, and then we're going to use this rule. I'm going to write over on the side here that a to the power of p times a to the power of q is equal to a to the power of p plus q. In other words, we add the indices together. So that means that I've actually got a 2 to the power of 3x plus 1 equaling 2 to the power of 10. Now I have it in the right format. I've got a base to a power equaling a base to the power, and the bases are the same. So now I can say, therefore, 3x plus 1 is equal to 10. And now I'm just going to do my basic equation solving. Take 1 away from both sides to get 3x is equal to 9, and then divide both sides by 3 to get x equals 3. So there we go. That's the solution there. Example 3. We have 3 to the power of 2x is equal to 81. Again, we don't have bases that agree in this case, so it's not in the right format, so we need to change it. And we can change it because, and this is just sort of like what you can do in your head, that 81 is a power of 3. And what you can do is you can basically go to your calculator and check it. What's 3 squared? It's 9. What's 3 cubed? It's 27. What's 3 to the power of 4? Oh, it's 81. So there we go. We now have 81 written as a power of 3. So 3 to the power of 2x is equal to 3 to the power of 4. Now we have base to a power equals same base to a power. Therefore, 2x is equal to 4, and divide both sides by 2 to get x is equal to 2. Example 4. We have 3 to the power of 2x equals 1 over 81. Now again, we saw from the last example that we know that 81 is equal to 3 to the power of 4. So we could certainly write it as 3 to the power of 2x equals 1 over 3 to the power of 4. But that is not enough by itself to suggest that 2x is equal to 4 or anything else. It's still not of the right format. That 1 over makes all the difference in the world. But we do have a rule which basically says a to the power of n is equal to 1 over a to the power of negative n, and a to the power of negative n equals 1 over a to the power of n. And it's this rule here, this second form, that we're going to use in reverse in order to get our equation looking as it needs to. So I've got 3 to the power of x is equal to 3 to the power of negative 4. So as you can see, I floated my 3 to the power of the 4 to the top and changed the sign of the index to negative 4. Now I have base to the power equals same base to the power. So therefore, 2x is equal to negative 4. And by dividing both sides by 2, I get x equals negative 2. And that's my solution for example 4. Now let's have a look at example 5. Now what makes example 5 different from the other ones is that, yes, we have a base to a power and a base to a power. So that's okay, but they are different bases, so it doesn't work. The other thing to note is that 4 cannot be risen to any power and make it equal to 8, and similarly with 8. So they are entirely different bases. However, if you think about it, you might see, okay, so there's my little thought bubble again. As you can see, I'm an awesome artist. Is that 4 and 8 have a common base of 2. 4 is 2 squared and 8 is 2 cubed. So what I do is I replace the number 4 with 2 squared. I'm putting in brackets deliberately. And I'm replacing 8 with 2 cubed. And 4 was raised to the power of x. And 8 was raised to the power of x plus 1. Now, I'm going to take this slowly so you can see it. But these steps, some of these steps could be done in your head if you're happy to. Using this rule that we've learned already, which is a to the power of p to the power of q equals a to the power of p times q, I can say that 2 to the power of 2 to the power of x is 2 to the power of 2 times x. And on the right-hand side, I've got 2 to the power of 3 times x plus 1. Be careful to have those brackets going. It's not 3x plus 1, but 3 times the whole of x plus 1. So on the left-hand side, I'll have 2 to the power of 2x. And on the right-hand side, by expanding, I'll have 2 to the power of 3x plus 3. And what we have here is a base to a power equals same base to a power. And so we can say, therefore, 2x is equal to 3x plus 3. And now we solve the equation. So when you've got an x on either side of the equation, we have to eliminate it from one side. So I'm going to take away 2x from this side and take away 2x from this side. The reason why I did it in that order is because that way my x's remain positive for the next step. So 2x take away 2x is 0. That's okay. I don't have to be afraid of having a 0 on the end there. And 3x take away 2x is x plus 3. And that means that x must be equal to negative 3. Okay, just by logic, but if you like, we can take away 3 from both sides to get x equals negative 3. So that's the solution for example 5, x equals negative 3. And if you want to, and this is true for all equation solving, if you find a value here, you can always substitute it in to make sure it makes sense. So we've got 4 to the power of negative 3. Does it equal 8 to the power of negative 3 plus 1? So you could put that into your calculator and make sure it gives you the same value. Okay, last example is example 6. Now, you will not be assessed on this in the test, so this is harder than what is assessable, but I thought you just might want to see what it looks like to do a problem of a slightly higher complexity. So the trick with this one is to notice that I've got 3 to the power of 2x here, and then I've got 2 lots of 3 to the power of x, which is really similar to this one. And I've got a plus 1 over here. Now, this almost fits a pattern. And again, remember, in Maths Extended, the idea is to grow into this sort of idea of being able to see patterns as they exist. And it's kind of like this one. It's kind of like a squared, minus 2ab plus b squared equals 0, because the a squared minus 2ab plus b squared is in fact a minus b all squared. So that could be useful. Now, we have a square here, 1, and with a little bit of unpacking, we actually have a square here as well. And we've got twice something in the middle here, so it nearly fits the pattern, and we'll just do a little bit of an extra step to show you what I mean for the rest of it. So if I go 3 to the power of x here, oops, I'll do it in the right color. Then 3 to the power of x is 3 to the power of x squared. Again, just using that rule, the power of powers rule, backwards. And the power of power rule says a to the power of p to the power of q is equal to a to the power of p times q. So here we have 2 times x. So all I've done is I've put an x inside a bracket there and then left the 2 outside. So if you go that way, you'll see x times 2 is 2x. I'll write the rest of it in the right color. Minus 2 times 3 to the x plus 1 is equal to 0. Now you might see from there that that's a perfect square match now, but I'm going to go one step further so you can sort of see it really stepping out for you there. Let a equal 3 to the power of x. Therefore, we have a squared minus 2a plus 1 is equal to 0. Now, this fits our idea of the perfect square because I have a square here, and 1 squared is 1, so I do have a square here, and I have 2 times a times 1 in the middle to give me 2a. So it does fit, so I can say, therefore, a minus 1 all squared is equal to 0. And what was a? Well, up here, we said that a was 3 to the power of x. So that means that 3 to the power of x minus 1 all squared is equal to 0. Now, just to keep it on the same slide, I'll just put the rest of the solution in the box over here. Now, if 3 to the power of x minus 1 all squared is equal to 0, it means that 3 to the power of x minus 1 must be equal to 0, because the only way I can get 0 from squaring it is if it's equal to 0 itself. Now, this is a solvable equation. It might not look like it, but it is. If I add 1 to both sides, I get 3 to the power of x is equal to 1. And I can change 1 into a base 3 as well, because 1, running out of room here, 1 is equal to a to the power of 0. That's that rule we've got. So that means that I can choose what a is, and if I set it equal to the power of 0, it's equal to 1. So that means I can say that 3 to the power of x is equal to 3 to the power of 0. Now I have the format I'm looking for, base to a power equals base to a power. And so therefore, x is equal to 0. So a fairly simple answer in the end, x equals 0. Okay, so that's 6 examples. You should copy these examples into your summary book and then solve the worksheets that are provided with this lesson. Okay, that's me out.